In this video, we show how to learn inverse statics models with online goal babbling as well as symmetry-based exploration of the configuration space. We propose and evaluate approaches which learn inverse static models without requiring any prior knowledge or controller. More precisely, we learn the mapping between desired configurations and the required talks with online goal babbling from scratch. For this 3R simplified humanoid arm, targets in task space are distributed on two grids. In the online goal babbling scheme, the corresponding joint configuration targets are employed. The robot is then trained to learn the required talks necessary to maintain the desired configuration targets. The main plot shows the targets in task space indicated by red crosses and the evolution of end effector positions indicated by blue circles during the training phase. The second plot depicts the evolution of the task space training error, which drops very quickly during the first few iterations. To visualize the generalization capability of our approach, testing targets within the previously defined grids as well as between the grids are selected and the robot is asked to maintain them. All testing targets are correctly maintained as indicated by the blue circles and the resulting testing error is less than 1 millimeter. However, online goal babbling can only provide locally valid inverse statics mappings. To obtain mappings which are valid for the entire configuration space, an extension of online goal babbling called direction sampling can be employed. To reduce the number of required training samples, the properties of the inverse statics mapping can be exploited as detailed on the following slides. Inverse kinematics models usually map from the lower dimensional observation space to the higher dimensional action space. So, IKMs are usually one-to-many mappings, meaning each pose can be reached by multiple configurations. On the other hand, inverse statics mappings map from joint space to motor space. Therefore, the dimensionality of the domain and codomain are usually identical. ISMs are many-to-one mappings, that is, multiple configurations require the same generalized force to be maintained. This many-to-one characteristic of inverse statics models, which are called symmetries, can be exploited to reduce the number of samples required for learning. In the left-hand plot, 4 configuration level sets are shown. Each level set comprises all joint configurations which require the selected motor torque tau1, tau2, minus tau1 or minus tau2 to be maintained. Each intersection of 2 level sets is marked and indicates a configuration which requires the same absolute values of the motor torques. These configurations are termed symmetric to each other. In the right-hand plot, the robot is shown in the configurations corresponding to the markers in the left-hand plot. The symmetric configurations can be discovered by applying different torque profiles to the manipulator, which all share the same absolute value of their terminal torque. As can be seen, the manipulator settles in different symmetric configurations when different torque profiles are applied. Thus, sets of symmetric configurations can be discovered. After discovering the symmetries, the functional relations between them are learned. Moreover, the SST, that is, the set of torques required to maintain all admissible configurations, as well as the BCT set, are explored. The training samples in learning can then be limited to this specific set of configurations denoted as BCTS. For each single configuration inside the BCTS, bounded by the depicted cuboid, there exist multiple symmetric configurations outside the BCTS. By exploiting the functional relations between symmetric configurations, the entire set of symmetric configurations is learned by sampling only one member of it. Thus, training is restricted to the green samples in the BCTS, and the total number of required samples is reduced drastically. Still, the inverse statics mapping can be learned with high accuracy for the entire configuration space, as indicated by the small deviations between targets and real configurations.